I'm investigating why a Sklearn Perceptron model shows consistently low accuracy, even after tweaking the learning rate. A to 0 and the maximum number of iterations. Max_iter. It's a puzzle I need to solve. I'm presented with multiple choice options that might explain the poor performance. Let's examine each one carefully. This is actually a good thing for the Perceptron. If the data points are easily separated by a straight line, or hyperplane in higher dimensions, then the Perceptron should be able to learn a perfect solution, given sufficient iterations. That's not likely to be the source of poor performance. This is a common problem. If one class greatly outnumbers the other, the Perceptron might become biased towards the majority class and perform poorly on the minority class. This could absolutely explain low overall accuracy. This is crucial for many machine learning models, including the Perceptron. If some features have much larger values than others, they dominate the learning process. This can slow down convergence or lead to a bad solution. Definitely something to investigate. The _random_state parameter is used for initializing the model's random weights. Without it, every run will have different starting weights and thus different results. It's like shuffling a deck of cards before every game. You'll get different outcomes each time. Inconsistent results might look like low accuracy. Therefore, this is a probable cause. The overall issue I am trying to solve is that the Perceptron model, a simple linear classifier, shows unexpectedly low accuracy. I'm investigating why a Perceptron model, a simple linear classifier in Sklearn, might show poor performance. I'll explore common reasons for this. This is the central question I am addressing. I need to identify the factors that could be causing low accuracy in the Perceptron model despite adjustments to the learning rate. A to 0 and maximum iterations. Max_iter. Let's dive into the reasons that could be responsible for the low accuracy. I will analyze each possible cause one by one. The _random_state parameter initializes the weights randomly. Without it, every time you run the model, weights start differently, leading to different results. RANDOMSTATE helps get consistent results, crucial for evaluation. Inconsistent results make it tough to know if the model's inherently bad or just unlucky with initial weights. Features with vastly different scales can confuse the Perceptron. Imagine trying to find a line separating points where one axis is in centimeters and the other is in kilometers. It'll be hard. Scaling puts all features on a similar scale, so the Perceptron can learn better. A highly imbalanced dataset can trick the Perceptron into focusing only on the majority class, ignoring the minority class. Think of it like this. A classroom with 95% boys, the model might predict boy almost every time, achieving high overall accuracy but failing at identifying the girls. This results in low accuracy on the minority class, impacting overall accuracy. I'm investigating why a Perceptron model, a simple linear classifier from Sklearn, isn't performing well. We're looking at factors that could cause consistently low accuracy, even after tuning learning rate and the maximum number of iterations. Imagine you have a dataset where 95% of the data points belong to one category, and only 5% to the other. A Perceptron might just learn to always predict the majority class, ignoring the minority class. This leads to high accuracy for the majority class but low overall accuracy, because the minority class is barely considered. That's why imbalanced data is a major suspect for poor Perceptron performance. The Perceptron is sensitive to the scale of features. Imagine one feature ranges from 0 to 1, while another ranges from 0 to 1000. The algorithm might get overwhelmed by the large-scale feature. Think of it like trying to compare apples and oranges without converting them to a common unit like weight. Scaling ensures all features contribute equally, helping the Perceptron learn better. The _random_state parameter initializes the random number generator. Without it, each run starts with different random weights. This means you'll get different results each time you run the model, making it hard to evaluate performance reliably. It's like flipping a coin instead of using a precise measurement tool. Setting _random_state guarantees consistent results for reproducibility and allows for fair model comparison. I'm tackling a problem where a Perceptron model, a simple linear classifier from Sklearn, isn't performing well. Even after I've tweaked the learning rate, (a to 0), and the maximum number of iterations, (max_iter), the accuracy remains stubbornly low. I need to figure out why. Let's brainstorm potential reasons for the poor performance. I'll examine several factors that could be hindering the Perceptron's ability to learn effectively and accurately classify the data. The (random_state) parameter initializes the weight of the Perceptron model. Without it, the model starts with different random weights each time you run it. This makes the results inconsistent and unreliable. Imagine trying to build a house without a blueprint. You'll get different results each time. Therefore, this is a likely culprit for the poor and inconsistent performance I'm seeing. Think of it like this: if some features are measured in centimeters, and others in kilometers, the Perceptron might get confused. The model needs features on a similar scale for proper learning. It's like trying to compare apples and oranges. Proper scaling is crucial for preventing slow convergence and suboptimal solutions, leading to improved accuracy. Imagine I'm training a model to identify rare diseases. If 95% of my data is from healthy people, the Perceptron will probably just learn to always predict healthy. This bias leads to poor performance on the minority class, and thus low overall accuracy. I see, you're asking about imbalanced datasets. Imagine you're trying to predict whether a person will get sick with a rare disease. If 95% of your data is from healthy people and only 5% is from sick people, a simple Perceptron might learn to just always predict healthy, achieving high accuracy on the majority class, but failing miserably on the minority class. The overall accuracy will look deceptively good, masking the model's poor performance where it really matters, failing to detect that rare disease. This is a problem, right? This highlights the limitations of the Perceptron. Let's talk about feature scaling. Imagine you're measuring both height in centimeters, small numbers, and income in dollars, large numbers. A Perceptron might give too much weight to the income feature simply because of its larger scale, ignoring the height data. This might lead to an inaccurate model. Think about it like this: you need to make sure all features are on an equal playing field to get the best out of the Perceptron. We need to pre-process the data before feeding it into the Perceptron. Okay, so the (random_state) parameter in Sklearn is used to control the starting point, initial weights, of the Perceptron algorithm. Think of it like shuffling a deck of cards before a card game. Each time you shuffle, you get a different starting order. Without a fixed random state, each time you run your Perceptron, the algorithm starts from a different random configuration, resulting in different outcomes and making it hard to compare results fairly. This doesn't mean the Perceptron is inherently bad, it's just that without a fixed random state, you are making a fair evaluation difficult, leading to unreliable observations. You would think you have a bad model, but really you just have different starting points. Fixing the (random_state) ensures reproducibility, which is crucial for fair comparison. Imagine you're trying to teach a dog to sit, but 95% of the time, you don't even try. The dog will likely never learn to sit. Similarly, if your dataset has a huge imbalance between classes, say, 95% of examples are from one category, the Perceptron will be biased towards that majority class, ignoring the others. This leads to poor overall accuracy because the model doesn't learn to effectively identify the minority class. It's like trying to find a needle in a haystack where 95% of the hay is painted blue. The (random_state) parameter in Sklearn's Perceptron sets the seed for the random number generator that initializes the model's starting weights. If you don't set this, the model starts with completely different random weights every time. This means your results will be inconsistent between runs. One time, your random starting point might lead to good performance, but another time, it might result in poor performance. The lack of consistency makes it tough to evaluate the model's true performance because you'll get a different answer each time you run it. It's like throwing darts at a dartboard blindfolded. The results are going to be pretty random, and you won't know how good your aim really is. Think of it like this: a consistent result will always give you confidence. Imagine you're teaching someone to bake a cake, but one ingredient is measured in grams while another is measured in kilograms. It would be super confusing, right? The same goes for the perceptron. If one feature has much larger values than another, the perceptron will be influenced more by the larger values, and the learning process is thrown off. This is because the model doesn't account for the differences in scales, leading to a suboptimal learning process and poor performance. Scaling ensures all features have comparable scales, which makes the learning process smoother, faster, and more reliable, allowing the perceptron to function properly.